Today, I plan to explain binary combinations of symmetry operations. A knowledge of binary combinations, or the products as these are loosely called, of symmetry operations is essential so as to describe these as members of a mathematical group. If A, B, C, etc. capital letters represent symmetry operations, a relation like A followed by B is equal to C says that binary combination of A with B is equal to C. What exactly does one mean by that? It only means the result of doing successive operations A and B on the molecule is the same as the result of doing just a single operation C. That is, the molecular look 1 on doing operation A it changes to look 2, and on doing operation B it can change to look 3. Now, the molecular look 1 can be changed to look 3 just by doing a single operation C. If such a relation exists, we say that the product of A and B is equal to C. In order to get binary products, it is very useful to describe the symmetry operations of a molecule with the help of Cartesian coordinate system. We all know that Cartesian coordinates are three mutually perpendicular axes, the x-axis, y-axis and the z-axis. With reference to these, any point in space can be denoted as, say, x1, y1, z1, where x1, y1, z1 are the respective x, y and z coordinates of that point. Let us hold the water molecule against the Cartesian coordinate system in this manner. This is the x coordinate, this is the y coordinate, not y axis, not coordinate, and this is the z axis. And I'll draw the water molecule in this manner. It is drawn in such a way that its C2 axis is coincident with the Z axis, so this can be called C2Z. And I have drawn it in such a way that the sigma V for water molecule, it's a plane bisecting it, it is coincident with the XZ plane. So sigma V can be called sigma V XZ. And the plane of water molecule where it lies on the board, the plane of the board which contains the Y and Z axis in it. So this plane, which we used to write it as sigma V dash, can be written as sigma V dash Y Z. Let us draw the Cartesian coordinate system in a more clear manner, for which I will get the help of a large cube divided into 8 miniature cubes. I have drawn an outline of the cube. The Cartesian coordinates are the x coordinate, the positive x in this direction. I say x-axis, not coordinate. This is the positive y-axis in this direction, and this is the positive z-axis The positive one I have drawn with a bold full line, and the negative of these can be drawn as broken bold lines in this manner. This is the negative x, this is the negative z, and this is the negative y. And you can see the three important Cartesian planes. Here is a plane, this is the xz plane. Here is a plane which is the xy plane, and here is a plane which is the yz plane. These are the three important Cartesian planes. Now consider a point, a general point in a general molecule as point P with the coordinates x, y and z. What will happen to these coordinates of the point P if this point, general point, is rotated about the z-axis by 180 degree? If a C2 is done on this point, it is very evident that this point will be shifted in this manner to this location. If this point is P, this will be P dash. And what are the new coordinates of P dash? It is very clear from our diagram. If this is x, y, z, where I have measured a distance of x along the x-axis, a distance of y along the parallel to the y-axis, and distance of z parallel to the positive z-axis. On reaching this point, P dash, the x-coordinate has been changed to minus x, and the y-coordinate has been changed to minus y, and z-coordinate remains as the same. Z-coordinate remains as the same. So we shall write x, y, z, 180 degree rotation about the z-axis changes the coordinates of the point to negative x, negative y, but z remains still positive. This result can be generalized. If the C2 axis is z-axis, the z coordinate does not change, but the other two coordinates change to their negative values. If such a conclusion is generalized, you can easily predict the change occurring for x, y, z on doing C2x. This x will not change, the other two will change to their negative coordinates. X will not change, the y changes to minus y and z changes to minus z. What about C2y? Here also y will not change, x will change to minus x and z will change to minus z. Then what about reflecting this point about the Cartesian planes? Imagine that the point P is reflected along this plane. This is the xz plane. XYZ is reflected about the xz plane. How is reflection done? Draw a line perpendicular to the plane, extend it an equal distance in the opposite direction, and place the point here. This becomes P2 dash. Here you can notice that the x and z coordinates of this point are not changing. This point is obtained by measuring positive x along the x-axis, but negative y along the y-axis, but positive z along the parallel to the z-axis. So the result will be positive x, y changes to negative y, and z remains the same. X is the same, y is minus, and this is positive. this is the style of reaching at this point. X coordinate has not changed, Y coordinate has changed to negative of Y, and Z coordinate has not changed. This result also can be generalized. How do you generalize it? Suppose the reflection is done about sigma YZ. Here the X and Z has not changed, only Y changes to negative Y. If the reflection is done about YZ, Y and Z will not change, but X will change to negative of that, minus X, Y, Z. And sigma XY plane, X and Y will not change. So it will be X and Y. Whatever axis absent in this notation will change to the negative value. This changes to minus Z. Cartesian coordinate system also helps to predict the change occurring to a point XYZ on inversion. How do you do the inversion operation? Draw a line to the central point, extend it an equal distance in the opposite direction, and place the point here, P3 dash. So from this miniature cube corner, it has gone to the cube at the back, miniature cube at the bottom back part, this point. So in order to reach this point, you have to measure X coordinate along the negative X axis, measure the Y coordinate along the negative Y axis, and measure the Z coordinate along the negative Z axis, parallel to the negative Z axis. The new coordinates of P3 dash are minus X, minus Y, and minus Z. That is typical of inversion operation. This point will change on inversion operation to minus X, minus Y, and minus Z. Now it is a simple matter to prove the binary product C2Z sigma H XY is the same as I. During discussion of improper axis S2, we had written S2 is equal to C2Z sigma H XY is equal to I. How is this result proved? This binary combination as equal to I proved. We consider a general point XYZ, do the operation C2Z on it, Z coordinate will not change, this changes to minus X, minus Y and Z. Now carry out the sigma H XY reflection in a plane perpendicular to this C2 axis. Here X and Y will not change of this point. So minus X will remain as minus X, minus Y will remain as minus Y because these do not change. But Z, the coordinate, the axis missing, will be changing to minus Z. And what is the single operation which will convert X, Y, Z to minus X, minus Y, minus Z? It is I. So it is very clear that the product of C2Z sigma H X Y is the same as the result of doing the operation I on the molecule. Cartesian coordinate system is not always useful in describing symmetry operations of other molecules. For example, in ammonia, the principal axis is C3 and it has 3 sigma V's. If at all you are drawing ammonia molecule against the Cartesian coordinate system, we can draw the Cartesian coordinates X, Y, Z and hold the ammonia molecule in this manner. One hydrogen here and another hydrogen here. This will be H1, H2 and H3. Principal axis of course can be coincident with the Z axis. So you may write C3Z. But what about the planes? At the most we can refer one plane with one of the Cartesian planes, but the other two planes will be bisecting the Cartesian axis, will not be merging with any of the Cartesian planes. So one plane at the most you may write as sigma v, say x, z, but the other planes cannot be done. So in order to get binary products of operations, we adopt some other method. For example, suppose I am interested to know the product of C3 sigma v of ammonia molecule. We have been drawing ammonia molecule as a projection. The H and H angle looks like 120 degree in this projection. The planes of symmetry are along S3N, we write it as sigma v. This is denoted as sigma v dash, and this plane is sigma v 2 dash. Here is a plane of symmetry which is called sigma v. Here is a plane of symmetry, sigma v dash, and this is the third plane of symmetry. All are vertical planes. C3 is the line of intersection of all these three planes. So these are vertical planes of symmetry. If you want to get this product, this is the starting point. You do the C3 here. It is anti-clockwise rotation by 120 degree. So the new molecular look with the labels on hydrogen will be H1, H2 and H3. Now you do the sigma v. This is the sigma v. So reflection will interchange these two, and H2 will remain there. So it will be H2 and H1 on this side, H3 on this side. Only H1 and H3 get mutually exchanged by the reflection of this plane. The other two atoms already lie in this vertical plane. So which is the single operation which can convert 1 to 3? We call it 3. What is the single operation? We compare 1 and 3. The location of H1 remains the same, but 3 and 2 got mutually exchanged. The lower H2 has come to the top, upper H3 has come down here. It is as if you have simply reflected the molecule about sigma v dash. So we can say that this product is equal to sigma v dash. This is how binary products in other situations are worked out. In our next video, it is appropriate to introduce the symmetry operations as members of a mathematical group.